Thank you. Okay, thank you all for coming. Today I'll be talking about the use of ocean OSSIs with the overall goal of trying to improve ocean model initialization in coupled prediction systems. And this talk will focus primarily on the impact of rapid response ocean profile surveys. And I'll specifically show examples from Eduard and Gonzalo. First, I'd like to acknowledge my colleagues in our joint AOML CMIS Rasmus Ocean Modeling and OSSI Center, or OMOC. So the putting together this OSSI system took a lot of work from all of us. So let's see here. Okay. So I'll spend the first 3 slides just briefly summarizing the OSSI system and where we stand with it now. In case anybody's not familiar, the key OSSI system components involve a nature run, multi-year validated free run, using a state-of-the-art ocean model in this case, which represents the truth. In this case, we use a HICOM model run at 0.04 degree resolution. Then the system has its ocean prediction system consisting of the forecast ocean model, which has to be different from the nature run model. In our case, it's a fraternal twin system using HICOM with a substantially different configuration from the nature run and also run at lower resolution. And our data assimilation procedure is a statistical interpolation system designed specifically for the HICOM Lagrangian vertical coordinate system. The other key component of an OSSI system is the synthetic observation simulation toolbox, where we simulate observations from the nature run. The key step there is to add realistic errors that are as close as possible to the errors in the actual observing system in the true ocean. Our system was initially evaluated and implemented in the Gulf of Mexico, and looking at the P3 ocean profile surveys for the Deepwater Horizon oil spill. And 2 papers were published for the Gulf of Mexico work in 2014 and 2015. The first one in JTEC describing the system, and the second one showing the application. That was published in Progress in Oceanography. And we've now expanded the system to our Atlantic domain, spurred by Sandy supplemental funding primarily for hurricane applications. And this just shows the domain where we've moved the OSSI system into. This is a sea surface height snapshot from our nature run. OSSI system validation steps. First of all, nature run evaluation. The nature run must reproduce ocean phenomena of interest within pre-specified error limits. It must have realistic mean climatology and realistic variability. And this work is now evaluating this nature run for the Atlantic region is now contained in 2 accepted papers, Karoflu et al. In Progress in Oceanography, and under Ladakis and et al. In Ocean Dynamics. And these papers show that with high confidence we can use this nature run based on how well it reproduces the climatology and the variability for simulating ocean observations. And these papers also show the scientific value of this nature run, looking at processes such as the interaction of a hurricane with the Gulf Stream and the impact of salinity barrier layers on ocean mixing as hurricanes force the ocean. So we're very happy with the nature run. The forecast model must be evaluated. The forecast model must neither be too similar to nor too dissimilar from the nature run. Basically, errors between the forecast model and the nature run, when they're run unconstrained, should have similar properties to the magnitude to errors that actually exist between state-of-the-art ocean models and the actual ocean. If the models are too similar or dissimilar, you will get biased impact assessments from an OSSI system. And the OSSI system itself is further evaluated by what we do is to run observing system experiments, simulation experiments with real observations, denying a observing system of interest to look at the impact on analyses and forecasts. Then we do this exact same experiment but using synthetic observations, and we want to make sure that we obtain similar impact assessments. And if we don't, then we know the OSSI system needs to be tweaked or redesigned or whatever. And our work there has been was very encouraging. That work is contained in a submitted paper, Halliwell 2016, in the Journal of Operational Oceanography. And these evaluations are contained in that paper, along with initial applications of the Atlantic Aussie system, evaluating components of the existing ocean observing system and glider enhancements during hurricane season. However, in the present talk, I'm not going to talk about any of that in this talk. Basically, this will be relatively new results. Our ultimate goal is to evaluate airborne ocean profile survey design using the Aussie system. An example survey design is shown here that I'll talk about later, where we basically collect synthetic AXPTs or AXCTDs at those locations shown, in this case for Hurricane Gonzalo. Then we evaluate the error reduction, additional error reduction due to the airborne surveys to see if they, to what extent they improve the ocean model initialization. There are three key things that we consider. First of all, we need to improve the accuracy of upper ocean heat content. If the upper ocean is too warm or too cold, that can potentially impact the intensity of a coupled forecast. And we also have to consider the horizontal distribution associated with boundary currents and eddies. We have large differences in heat content associated with these features in some regions of the ocean, particularly like the Gulf of Mexico and the Northwest Caribbean and the Atlantic. We also want to improve the accuracy of upper ocean stratification. If their stratification is too weak or too strong, that impacts how accurately the ocean model will entrain colder water into the mixed layer. And again, we have to consider both bias and distribution associated with ocean features. Overall, we also need to improve the representation of ocean dynamics, because the background vorticity associated with boundary currents and eddies affects the magnitude and structure of forced ocean cooling. And a lot of work has been done by Benjamin Chimes and Nick Shea in this regard. So we need to improve in all of these aspects to try to give the ocean model the best chance to provide good SST forecasts in a coupled system. And in this talk, I'm going to focus on 4 model fields that are important for the hurricane problem. The tropical cyclone heat potential, which also known as ocean heat content relative to the 26 degrees Celsius isotherm, which is used operational to represent the potential ocean impact on intensity. Delta T between the surface and 100 meters at SST minus 100 meter temperature provides a crude measure of temperature difference within and below the mixed layer, a crude representation of vertical structure and how accurately the ocean model reproduces that. Sea surface height, of course, is associated with the ocean dynamics and the associated quasi-geostrophic surface flow field. Depth of the 20 degree Celsius isotherm, which represents the main thermocline depth, and is also used as a proxy for eddy and boundary current structure. It tends to outline the eddy and eddy structures and boundary current paths. So looking at how well we're improving these fields will give us an idea of how well we're hopefully improving the ocean model initialization. And we're going to look only at the assessments based on error reduction in the ocean analysis fields. We will be eventually extending this work to look at how that actually impacts coupled hurricane forecasts. But I'm going to focus only on the ocean part today. Now, a general approach, there is a problem with evaluating these pre-storm ocean surveys like the one I showed a couple of slides back. They cover a fairly limited region, which restricts the ability to perform rigorous quantitative statistical analyses of these surveys with high statistical significance. Fortunately, in Aussie system, you're not constrained by things like cost or how many instruments you have or anything like that. So before I get to actually evaluating these synthetic surveys, I'm going to perform idealized Aussies, evaluating the impact of ocean profilers over an extended spatial region and over an extended period of time, a very large ocean region, so I can really look quantitatively at how ocean profile surveys will correct these ocean fields. And in this case, the Aussie system allows us to take advantage of the high-resolution three-dimensional representation of the truth provided by the nature run. And I'm going to use these idealized Aussies to perform rigorous quantitative analyses of the accuracy with with which the horizontal structure and model fields is corrected for different profiler deployment strategies. And then I'll take the results from these idealized lattices, and then we'll move on to the actual Eduard and Gonzalo experiments, and this will help interpret those results. Now, idealized experiments. I became ambitious, and I'm applying 1,000 meter synthetic CTDs daily within a large 15 degree by 15 degree box, which is outlined there in the open Atlantic to the north of the islands. And the CTDs will be deployed at 3 different horizontal resolutions to give us an idea of how dense profilers should be to achieve adequate correction of ocean fields. Several experiments are run. The forecast model is unconstrained. And that's from a long model run. The control assimilates four major components of the existing operational ocean observing system: altimetry, Argo, XVT, and SST. That experiment started on March 1st, 2014, run through hurricane season. And then there are experiments run at 3 different resolutions. The 2.5 all is run with the CTDs at 2.5 degree resolution within the box, in addition to the existing ocean observing system. 2.5 CTD is just assimilating the CTDs only, and the same is done for 1 degree profiler resolution, 0.5 degree profiler resolution. And before getting to the quantitative statistical analyses, we'll just do a gee whiz look at what happens in terms of, in this case, this is tropical cyclone heat potential. Remember, the nature run represents the truth, and in this case, compare 4 experiments to the nature run. First of all, the upper left panel is nature run minus control. This is assimilating existing ocean observing system. And you can see that substantial error still remains in this case. Now, if CTDs are added at 0.5 degree resolution in the upper right, you can see a large correction in the ocean field. And what you see also is that the remaining residual errors have very small horizontal scales, so the CTDs are correcting larger scales. And if they're deployed, the CTDs are deployed at coarser resolution, you see less and less improvement. Now, this is a case where we assimilate the CTDs only. So the upper left panel shows the errors, nature run minus the forecast model. Of course, they're much larger since the control, the assimilation and the control run reduced errors. This shows you the actual errors between the forecast model and the nature run with no assimilation. And here again, you see the correction very substantial for 0.5 degree resolution, leaving only small scale variability. And one thing that's important to notice is that the error reduction due to deploying your instruments is really confined within the area where you deploy the instruments. It really doesn't extend away from the boundaries at all. So hoping to correct ocean fields at a large distance from where you're sampling is, and I'll show other cases of this, is not really to be expected. But this is just a gee whiz look. Now, to perform rigorous statistical analyses, I'll move on to that now. I'll look at several different statistical analyses here. The Breyer skill score is shown, which is based on the mean square difference, as shown. The skill score is given by 1 minus MSD sub E over MSD sub R, where E is the experiment being evaluated and R is the reference experiment, which will always be the unconstrained forecast model in this case. So the skill score of 1.0 is perfect, 0 is no improvement, less than 0 is degraded. And of course, I'll also be looking at the corrections of mean bias and RMS error, and then I'll also, but the main thing I'm going to do with this large domain is really take a look at how the correction, the properties of the correction in zonal and meridional wave number space by performing spectrum analyses. what scales are being corrected by different densities of ocean profiler deployments. And spectrum analysis will be performed in both in zonal and meridional directions. The evaluations conducted from mid-July through mid-October using all experiments. So and daily, using daily model output. So on each day, individual zonal and meridional spectra are calculated. The zonal spectra are calculated at each meridional grid point, and the meridional spectra are calculated at each zonal grid point, and averaged both zonally and meridionally. Then these are further averaged over all days in the 3-month window. So significant degrees of freedom are achieved by the spatial and temporal averaging, so I don't have to average across wave numbers. So we can have a very detailed spectrum. We can resolve a very detailed spectral structure looking at this. And I'm going to be presenting spectral density of the what I call the error spheres, which is the nature run minus the experiment. Nature run represents the truth. And I'll also present the squared coherence between the nature run and the different experiment fields. And to determine error bars, degrees of freedom are estimated as the number of integral space scales times the number of integral time scales based on the autocorrelation space and time scales. And for TCHP, this is an example of all of these statistics I just mentioned. The tables on the left show the skill scores and the RMS errors. For in this case, it's the forecast model, control run, and the 3 different all experiments, which is existing ocean observations plus the CTDs. The spectral density and zonal spectra are shown on top, meridional spectra on top. The right panels show the squared coherence. And of course, the error spectrum is largest for the forecast model, which is shown in black. The red curve is from the control run, and what you can see, of course, is substantial error reduction and significant squared coherence for that. But if you add the CTDs, there's really very little improvement at 2.5 degree resolution, more improvement at 1 degree resolution, and substantially larger improvement at 0.5 degree resolution. And in terms of skill score, you can see substantial error reduction. And in terms of the RMS difference, you see the control, for example, the control run, RMS error is reduced by about 50%, and you get another 30 to 40% reduction by the time you deploy CTDs at 0.5 degree resolution. The vertical lines in the squared coherence plots are basically, they show basically the approximate Nyquist wave numbers for the 3 different deployment scales. Nyquist wave number is twice the horizontal separation of the instrument. So the Nyquist wave number is about 1 degree for the 0.5 degree deployment, and then again shown here for the 1 degree deployment, 2.5 degree deployment. And what you see here, and I'll show this in other plots, is there's a tendency for the significant corrections that only occur at wave numbers exceeding the Nyquist. So you're not correcting scales smaller than the typical Nyquist wave number based on separation distance. Now I'll show why that, an example of why that happens later. This is also for TCHP, but this is only assimilating the CTDs. So the forecast model and control run are the same, but you see generally very small corrections generally for the 2.5 degree deployment, and by the time you get the 0.5 degree deployment, the CTDs alone correct the fields better than the existing ocean observing system. Now here you can see one clear point that comes out, especially here in the meridional spectra. You can see that the significant coherences are only occur at scales larger than the Nyquist wave number. So you can see the 0.5 degree, 1 degree, and and 2.5 degrees. So when you're designing experiments, any experiments where you're deploying instruments over a given area, you have to keep in mind that you're not going to correct scales smaller than twice your typical separation. And that can have negative impacts on ocean model initialization and forecasts. Very quickly, I'd go through these quickly for the other three variables because results are generally quite similar. This is delta T between the surface and 100 meters. What you see is that the upper ocean the temperature profile is substantially corrected by the assimilation. Again, not so much for the 2.5 degree deployment, but substantially for the 0.5 degree. And the same for assimilating CTD alone. Again, seeing the dependence, the confinement of the improvement to scales larger than the Nyquist wave number. SSH is an interesting, representing the surface eddy structure, and there's an interesting result that comes from looking at the control run squared coherence. And what you see is that in the meridional spectrum, you have higher coherence at scales between 150 and 300 kilometers than you do for the zonal squared coherence, and that's because altimetry, we assimilate altimetry along track, and along the track you're resolving smaller eddy scales, but cross track you have the separation of tracks, and this shows up quite clearly when you, because the control experiment, the eddy structure is primarily constrained by the altimetry, and you see that anisotropic correction that results. Of course, as you can see from the purple curve, if you deploy CTDs at high resolution, you can correct the smaller scales that altimetry can't. So the advantage of, altimetry can only take you so far, and you can substantially correct smaller scales if you deploy ocean profilers at sufficiently high density in the horizontal. SSH, this is basically SSH all. The 20 degree isotherm depth, again, you see basically results similar to the other fields. So basically all of these fields that are relevant to the hurricane forecast problem are effectively corrected by deploying CTDs. And this again is CTDs alone. And so I guess I've beaten this dead horse enough. So I'm going to go on to bias reduction. I show the bias for these experiments for two fields, SSH and H20. It turns out that the two other fields, heat potential and the temperature difference, the mean bias between the forecast model and the nature one was very small. So there were inconclusive results for that. But there were significant biases in SSH and H20 that were corrected by this assimilation. And on top you see the biases in meters for the forecast model and the control. And then for the experiments assimilating CTD plus control and then CTD alone. And what you see is compared to, for example, the if you look at the 2.5 degree cases, both the all cases and the CTD alone, the 2.5 degree resolution allows you to make a large correction in bias correction. You only saw a weak correction in the structure of the field, and but for bias correction, coarser resolution CTDs can very much be very helpful to reduce biases. And here you see that basically 20 degree isotherm depth has a large positive bias that's reduced. Associated with that is the steric component of SSH, because the deep 20 degree isotherm depth is associated with the warmer water column and thus higher SSH. So if you correct the water column temperature, as the assimilation does here, you do also correct the bias in SSH also, as you reduce the average density of the water. or increase the average density of the water column. And this one point to make here is that the 2.5 degree resolution, the fact that you have effective bias correction, also sort of applies to the Argo floats. Now, in other work I've done simulating Argo floats, which typically have 3 degree separation, 10-day sampling. They're not effective at correcting eddy scale structures, which is obvious, but I've seen significant bias reduction over large scales by simulating Argo. So that's the primary value in terms of Argo and ocean assimilation. Okay, I showed in all those spectra and coherences that the smaller scales are not corrected. Why are smaller scales not corrected? And basically I show the analysis equation here that we solve. And the key takeaway here is that the background error covariance matrix, P sub B, which we multiply by a localization radius function to prevent large or significant correlation of long distance from influencing the solution. This function, resulting function, is what spreads the innovation matrix across model space to determine the correction field. And the error covariance matrix tends to have a smoothing effect. And it tends to smooth the correction field. And we can take a look at this actually, given that we have the high resolution representation of the truth in the nature run. I can show an illustration of that. This is a case where a temperature salinity profile was assimilated on 2 consecutive days at the location of the white dot. On the left, you see the resulting correction after 2 days. And again, the correlation function tends to be smooth and fall off. Their scales of correlation scales are typically a couple or 3 degrees. Whereas if you look at the difference between the nature run and the forecast model, the error field, and this is actually the negative of the error field, but you can see the structure of the error around that white dot is quite different from the correction performed that actually occurred due to the assimilation. And I've seen this in many other cases. Basically, you smooth out the smaller scales, and the error field contains, you can see the small frontal type boundaries in the error field that just are not corrected. So the result is instruments spread too far apart, or a single instrument just will not correct scales, smaller scales in the field in terms of eddy structure. They can reduce bias regionally, but this is a limitation. And what this tells you is that multiple profiler deployments are really needed to correct eddy features. So if we're doing rapid response surveys ahead of a storm in the ocean, dropping 1 or 2 widely separated ocean profilers won't really help correct anything. In fact, this actually, to summarize these idealized Aussie results, we'll tell the story. The only correct, profile surveys will only correct horizontal scales that exceed the Nyquist wave number based on typical profile separation. And the corrections that I showed are strongly confined to the region directly sampled by profilers. So you can't really, if you want to correct an area, you have to sample the entire area. Bias reduction is effective even with coarser profiler sampling. Really, when separation is typically 1 degree, you almost max out in terms of how much bias is reduced. What kind of guidance now do we get from designing free-storm ocean profile surveys? It's best to drop multiple profilers over as large an area as possible. Resolution of the profiler should be less than or equal to 1 degree to substantially correct mesoscale structure in model fields. 1 degree is adequate, ½ degree is better. Correction of submesoscale and frontoscale structure will require very high resolution sampling. And since that's not well corrected now, this points to really potentially large importance for the SMOS altimeter, which will be able to provide 2-dimensional SSH anomaly fields with order 10 kilometer or less resolution, so we can perhaps begin to look more accurately correct these smaller scales with that altimeter in the future. But right now, you just need to drop profiles at very high resolution to correct those smaller scales. So finally, I can get on to pre-storm rapid response surveys. And I showed this before for Hurricane Gonzalo. A one-day airborne survey that drops AXCTDs at the points shown. I show again for the same 4 fields I've been talking about. In color, you see the correction that occurs by adding AXCTD to the control experiment, assembling the existing ocean observing system. And if you look at RMS errors and skill scores, obviously large correction is provided by the existing ocean observing systems, but there's additional, significant additional correction is provided by adding the AXCTDs in this case. Now this is for a single day AXCTD survey. What happens if we do 2 consecutive days where the strategy is to kind of fill in the gaps, and what you have is somewhat more effective additional correction as expected by the AXCTDs. It's hard to do a consistent visualization of what's happening here, so I'm going to look at these issues in using a Taylor diagram for the 2-day AXCTD survey for Gonzalo. What I show here are the 3 markers, the shapes. Diamond is unconstrained forecast model, square is control, circle is control plus AXCTD. The 4 colors show the 4 different variables. Now the fields were all normalized by the nature on RMS amplitude so that these different variables could be placed on the same Taylor diagram. And in the lower right, you see the large blue dot. Its fields are identical. That is where the point should lie. And you see that along the azimuthal axis, you have correlation coefficient, which would be 1 in that case. RMS amplitude would be 1 in that case, which is the x-axis. And you can see the concentric circles, which was RMS difference between the fields. Now, for all 4 variables, if you look at the 4 diamonds, the unconstrained forecast model for H20 and delta T and heat potential and the SSH. Of course, insignificant correlation, the errors are quite large. If you look at the squares of the control experiment, you can see substantial improvement for all variables by assimilating the existing ocean observing system. And here you can see the additional improvement that you obtain by adding the AXCTDs to that. And it's a modest additional but significant additional improvement for most fields, for example, H20. For the case of SSH, we don't see a significant improvement. I have not looked into why that is so different from the other variables. But anyway, the improvements due to the pre-storm airborne surveys do show up generally in the Taylor diagram. And I also showed before the 1-day AXCTD service, the AXCTD survey versus the 2-day, and we can look at the difference here on the Taylor diagram, where the square, for example, is for the 1-day survey, and generally you can see a modest additional improvement, except for SSH, if you sample for a 2nd day. The good news is, though, that most of the improvement is achieved by a single 1-day survey, which is, for cost purposes, is probably a nice result to see. What happens when we look at, when we did the same 2-day survey, we would use AXBTs, sampling only the upper 400 meters of the water column. The answer is generally slightly degraded results. You can see it more clearly, but very slightly. You can see here on the Taylor diagram, square is AXBT and circle is AXCTD. For H20, there's a very slight improvement, and for SSH, there's a very slight improvement, not too much for the other 2 variables. So only a very slight improvement for using CTDs versus BTs in this region. So at least in this particular region, AXBTs are quite adequate and I should point out this one reason this is true, even though AXBTs don't measure salinity, when we assimilate, we use TS correlations to generate synthetic salinity. So we are assimilating salinity also for the AXBT case. It's just somewhat less accurate than you would get from the actual CTD measurements. But the impact is really not that large. And one point I need to make is that this is somewhat different from the result we obtained in the Gulf of Mexico, where AXBT versus AXCTD produced a larger difference, or in other words, AXCTD assimilation produced a more significant improvement versus AXBTs than shown here. So these results are region independent, obviously, and more work needs to be done in different regions. Just to go away from the airborne type surveys, we've heard about the interest in picket fence type deployments. For example, some surface drifters with containing thermistor chains deployed across a predicted track. And I just ran a case here where there were 3 picket fence tracks. Each of these, at each point, thermistor chain sampled down to 150 meters. And as you can see here, there's very little change in the depth of the 20-degree isotherm, which is substantially deeper than 150 meters. But other fields show some modest additional correction. So there is modest additional correction, but it's not large. So it remains to be seen how effective picket fence type deployments will be. Quite often, if you just deploy one picket fence deployment, you don't necessarily cover that much along track distance in terms of correction. So it's not likely you'll see a lot of impact on any hurricane intensity forecast. The name of these 3 lines, the lines are separated by close to 2.5 degrees latitude. And you can see for pre-storm surveys, the correction is relatively confined generally to the region of the actual instruments, and you don't really fill in a good 2-dimensional correction. So I can quickly show a couple of results from Edward, where for single-day survey, results tend to be fairly similar in terms of the modest additional improvement by sampling the AXCTDs. Same for a 2-day survey. In Edward, there was an actual P3 survey ahead of the storm conducted on about 12 September 2014. And so what I did was sample the same instruments used on that survey from the nature run and ran an Aussie comparison on the type of improvements gathered. And what you see in terms of skill score, you do see, especially with heat potential, although the corrections are relatively confined again to close to the actual sampling locations, there was an improvement in skill score overall in the region sampled. So there's some improvement that's detected using the Aussie system in this case. But again, it shows it emphasizes the advantages of covering as large an area as possible, and in both dimensions trying to sample as densely as possible within at least around 1 degree separation or less to really have the maximum impact of these types of surveys. Okay, brief summary. Pre-storm, they can reduce errors in initial ocean model fields. And each individual ocean profile measurement corrects ocean fields only over a limited area. Relatively high horizontal sampling resolution is important to achieve significant corrections, and large area coverage is desirable. The larger, you're limited to the area you sample, so if you want to try and improve as much as possible any impact on forecast hurricane intensity, the larger area you sample, the more likely you will have positive results. One caution with the results shown here is that these results are only for Gonzalo and Edouard, the 2 storms that presented themselves during the Sandy supplemental period. The ocean signal out in the open Atlantic is substantially weaker than it is, say, in the Northwest Caribbean and Gulf of Mexico. So corrections shown for these storms are likely to be smaller compared to these other areas where you have larger ocean differences in heat potential and other fields. So we need to continue this work for other ocean regions and other storms to have a good handle on what the impact of these pre-storm surveys will be under a wide range of ocean conditions. Ongoing and future OSI work. Again, extend the rapid response observations to other storms. And also what we want to do is directly test the impacts of rapid response observations in coupled hurricane forecasts. We actually developed the ability to do this, but before I could have this particular work translated into performing actual coupled forecasts, we lost Jilly Dong, our postdoc, who was going to do that work back to EMC. So we need to fill that gap because we have the ability to actually evaluate impact assessment, ocean observations in the ocean, and then use our different ocean fields to initialize the coupled forecast model and actually then see what difference it might make on intensity. So a lot of work to be done in the future on that. And just some final words on the future direction more generally of the OMOC-OSI system, what our group tends to do. We're going to be extending our OSIs to look at other applications. We can look at the transport, dispersion of oil, marine debris, search and rescue, optimum ship routing. There are a lot of potential applications where evaluating ocean survey strategies can potentially be very helpful. We'll be working in the near distant future to expand our OSI system capabilities. For example, include new data assimilation methodologies so we can look at the sensitivity of our results to the actual data assimilation method used. And one thing we're spinning up on now is to try to expand our OSI system from regional to global capabilities, where we begin to look at maybe global climate issues and monitoring with the OSI system. We're beginning that work, and I'm cautiously optimistic that when I'm here this time next year, I'll be talking about that, but we'll see how things go. There are a lot of potential pitfalls to get through. And that's it, so I'll take questions. Would you like a repeat? Let me go back to slide 1. Okay. Yes.
Okay, so if I have a fixed number of instruments, there's this inherent kind of tension between wanting as big coverage as possible and wanting as high a resolution as possible. Is there some way of quantifying the balance of those two that would be ideal?
We can we can design any kind of, the OSI system, we can be very flexible. We can do various scenarios, and I can talk to you about that because we have the ability to, look, we haven't yet, but.
And one more quick question. The Rossby radius for clinic is probably a little less than half a degree in this area?
It's less than that.
So you suspect if you kept stepping down the resolution to a third of a degree, 10 degrees, that you would have kind of seen a leveling out of the value?
Quite possibly, yeah. Well, the nature run probably doesn't resolve scales less than 30 or 40 kilometers anyway, so eventually you need a higher resolution nature run if you're going to get to the sub-meso scale. Yes?
I was curious about the way that you defined the drifter thermistor chain. The picture that you showed me looked static. Were they allowed to?
It was static. Because we haven't built that in yet. It's easy to do to actually advect them with the flow. Given the fact that they were only in the moderate for 2 days before the storm, it probably didn't make a big difference with this first look. But in general, if we deploy these especially for days and longer, we do have the ability to advect them.
Because I thought it might provide multiple range of scales because they.
Oh yeah, you could, yeah.
And then you could also use them to correct the velocity field.
Yep, exactly. Yes. And if you have something like the liquid robotics wave glider, for example, you can 2 or 3 days before a storm, you might try to move them closer together at certain locations relative to the forecast track. And there's a lot of games to be played in. And of course, you can always set up your OSI system to test that before it's done. Yes? Frank? Yes.
When you talk about the DA methodologies, right now you don't have any covariances in the background, right, that you're taking advantage of. You said you're using salinity lookups instead of looking at...
Oh, the salinity, in terms of the profile simulation, if we have a temperature profile, we have to provide a salinity because since our model is a layered...
The model's not built to take advantage of that relationship within the model. You
Well,
have to provide it
yeah.
externally.
Right. Well, our model, basically it's a layered model with isopycnic interior coordinates. What we do with any profile, if you have NHES profiles, we remap it to the hybrid coordinate space, which includes layer thickness in the ocean interior with constant density within each layer. So we simulate it that way, layer by layer. For a temperature profile alone, we have to provide a salinity to do that remapping.
Right, but in the model itself, it has a natural tendency on how, if you looked at an ensemble runs, there's a relationship between TNS in the model.
In the model, yes. Right now, we're only using the climate. Not yet. We're using the climatologies.
And all that stuff,
Mm-hmm.
you take advantage
That could be an exercise to improve our results. But,
yeah,
right. Mm-hmm.
Right.
Anybody else? Billy?
I'm curious about the conclusion that the XCTDs did not offer more correctness compared to XPPs in the area you were shown today.
Yeah.
And you said that in the Gulf of Mexico they actually did more.
Yeah.
So that puzzles me a little bit. I was trying to think of, do we understand something about the ocean structure of the domain?
Oh, yeah.
In the Gulf it was really on the ring.
Loop currents and rings were dominating the signal there, and so it's just different. I haven't looked into it in detail, obviously, but it's just
Yes,
right.
it would not really be important there. So why did the XCTDs,
Mm-hmm.
matter more? That's what
Good question. The XCTD was slightly better for two variables and almost the same for two others.
Close to similar, so saying that it's not that important.
No.
It was better in the Gulf, even though that's
It was better.
Right.
Better in the Gulf, yeah.
That's what but it is that, the HTTs and the XCTDs aren't that different in the open Atlantic because there's not that much stuff.
And maybe we know the climatological TS relationship might be really good there.
Yeah, that's the other thing, because
Mm-hmm.
you're using it on
Yeah. Anybody else? Okay, I'm done.
Catch you later, kiddo.
Okay.
I think having those drifters actually drift to it, make a big difference.
It might. This is the first look, obviously.
You put down one line,
Yeah.
and then they move.
Yeah.
And they're moving with the structure.
Exactly. And future work. Yeah.
They're helping you get a map
It's
of the actual
yeah.
structure.
Right. But for 2 days, it's not a huge difference. Maybe a few kilometers here and there. But anyway.
Well, one of the things that we don't know is how soon ahead do we have to do it.
Yeah. And again, we'll do experiments for that. Yeah.
Okay, right now we're trying to put it down exactly 24 hours ahead. We have to know the forecast track.
Yeah. So yeah, we can design experiments. What time interval do you have before you lose your initial?
Well,
Yeah.
the other thing I'm concerned about is, the cost of AXP